Here is a combined summary of the 2 pages. The paper presents a novel framework for the study and design of AI-assisted musical devices, referred to as AIMS. The authors begin by introducing a taxonomy of these devices, categorizing them into 6 main categories: musical instruments, music processors, music generators, music recommenders, feedback systems, and educational devices. Each of these categories can be further divided into subcategories. For instance, music generators can be instrumental, vocal, or combined, while music recommenders can recommend music based on the environment or the user's state. The authors also propose a set of scenarios and personas using Nielsen's user-centered approach to shed light on the design ideas behind different musical devices. This approach evaluates devices in terms of functionality, usability, and user experience. The scenarios and personas introduced are meant to illustrate the design ideas behind different aims, highlighting the importance of user sentiments in the design process. The framework presented is a valid tool for the study of intelligent musical devices, covering a wide range of possibilities and uses. The authors aim to create a comprehensive framework that encompasses all, or at least a very wide part, of intelligent musical devices, helping to design, understand, and study them. The paper is structured into sections, including materials and methods, results, and discussion, followed by conclusions. The taxonomy proposed is complete, easy to apply, and useful, providing a classification system for aims. The authors emphasize that a device can fall into several categories, making the taxonomy flexible and adaptable. The paper also highlights the importance of considering machine learning as one of the possible alternatives for designing layers of a complete system, rather than an independent agent. Overall, the framework presented provides a novel approach to the study and design of AI-assisted musical devices, offering a comprehensive and structured way to understand and categorize these devices. This research paper explores the potential of AI-assisted musical devices in enhancing user experience and accessibility for musicians with disabilities. It presents various scenarios where AI technology can be integrated into different aspects of music, such as instrument design, audio processing, and educational aids. The first scenario involves Mike, a bass player who suffers from a hand injury that limits his ability to play. An AI-assisted robotic mechanism is developed to detect which string Mike is fretting with his left hand and pluck it accordingly. This device also adapts to the tempo and genre of the song by varying rhythms and patterns, allowing Mike to continue playing in his band. In another scenario, Toby undergoes music-supported therapy after a stroke that affects his right hand mobility. He uses a set of MIDI drums controlled through hand gestures detected by electromyography signals, EMG. As Toby progresses in his recovery, the rehabilitation device dynamically adjusts the level of control he has over the drums, keeping track of his progress and sending reports to his therapist. Mary, a beginner concertina player, uses an intelligent didactical concertina called Inteltina that assists her in producing a nice sound. The instrument's assistance decreases as Mary's playing capabilities improve, preventing her from becoming reliant on the device. Sarah, a singer, uses an AI-enhanced version of Antares Autotune for pitch correction during her performances. She is satisfied with the natural feeling and minimal delay provided by this hardware-software implementation. However, she wishes for a similar pitch correction in a smaller, cheaper device. Kira, a production engineer, frequently uses the deep learning-based LV2 Deep AFX plugin framework to control her DAW and introduce various effects. She hopes to have an embedded version of these plugins for live performances. The paper also discusses the creation of new digital AI-supported musical instruments, like the Theremin, which combines the original theremin concept with an AI-based gesture recognizer to change the timbre of the instrument according to hand gestures. This reflects the creation of new digital AI-supported musical instruments, which can be fun to build and play but challenging to create a community around them. In terms of audio processing, Saul, a professional guitar player, desires a Mesa Boogie Mark V amplifier but finds it too expensive. His friends from a startup company design an AI system that can emulate the Boogie using a Coral Edge TPU accelerator. After testing the device, the company begins selling the Boogie Boogie pedal. The paper concludes by highlighting the potential of AI-assisted musical devices in enhancing accessibility and user experience for musicians. It emphasizes the importance of understanding the needs of users with disabilities and the role of AI in creating innovative solutions that cater to these needs. In the realm of music generation, two scenarios are presented. The first, on hold scenario, involves Peter, who owns an online business and uses AI-based music generators like Ava and Computoser to create copyright-free music for his customers on hold. This music is dynamically changed based on expected waiting time, time of day, and other circumstances. The second scenario, singing elevator scenario, introduces Mia, a design engineer at a large elevator company. She uses the OpenAI jukebox generator to produce songs tailored to the characteristics of the building, residential, commercial, neighborhood, etc., making the elevator a personal feedback Amy. The Emotowatch scenario presents Sam, a sports and music enthusiast who enjoys running while listening to music. His smartwatch, equipped with an app, selects songs based on his mood, which is determined by physiological indicators such as electrodermal activity, heart rate variability, and peripheral oxygen saturation. In the Let There Be Light scenario, Nico attends rock concerts and uses a PixMob LED wristband that can be controlled by an AI-based controller, making it an Amy. The Teach and Play scenario again, and the Magi Flute scenario, are both educational musical device scenarios. The former was previously discussed in subsection 2.2.1.3, while the latter introduces John, a 13-year-old with a moderate learning disability. His music teacher recommends using the Magi Flute, an accessible digital musical instrument, ADMI, that is an electronic wind instrument, EWI, similar to a recorder. The Magi Flute uses sensors for wind and touch pressure, controlling a synthesizer through an embedded deep learning system and assisting John with his iPad to remember what to play and how to play it. This device also has the capability to automatically correct what John is playing when configured accordingly. The Magic Flute scenario is presented, featuring an electronic wind instrument, EWI, called Magic Flute, played by Ellen, who has a spinal cord injury. The authors propose a generic architecture for designing musical devices, consisting of 5 layers: user stimuli capture and processing, embedded learning, music adaptation, music production, and user feedback. This architecture is illustrated in Figure 4. The authors then discuss the implementation of Thera-Iman, an AI-assisted variation of the theremin instrument. The block diagram of Thera-Iman is shown in Figure 5. The instrument uses open theremin antennas and a camera to capture hand gestures, which are processed using a Raspberry Pi board and a teachable machine accelerated with a Coral Edge TPU accelerator. The system classifies gestures into trained classes, and the sound production layer is implemented using Sonic Pi and Open Sound Control (OSC) protocol. The Thera-Iman system produces audio as a function of hand positions and gestures, captured by the antennas and camera, and recognized by the teachable machine. This implementation demonstrates the suitability of the proposed generic architecture and the usefulness of the framework presented. The authors argue that this approach can be used for simpler and more complex devices, citing the example of the singing elevator that uses various sensors to create music. The proposed architecture and Thera-Iman implementation showcase the potential of AI-assisted musical instruments for individuals with disabilities, providing a systematic framework for building and describing such devices. The use of machine learning and computer vision enables the creation of novel musical instruments that can be controlled by diverse user inputs, including hand gestures and head movements. Here is a combined summary of pages 9 and 10 of the research paper. The FAIME framework is a simple yet effective approach for designing AI-assisted musical devices, providing clear insights into the design process. This framework consists of a stimuli layer, a stimuli adaptation layer, a learning layer, and a production layer. The Emotowatch, for instance, uses wearable device sensors as a stimuli layer, preprocesses them in the stimuli adaptation layer, estimates the user's emotional state, and selects the music in the learning layer, outputting the music through a player in the production layer. The paper presents a framework for the classification, understanding, and design of AI-assisted musical devices, showcasing a wide range of devices that can fall into this category, including accessible instruments for disabled musicians and alarm clocks for people with sleeping disorders. A detailed implementation of a variation of the theremin, a successful musical instrument designed in the 1920s, is also presented. The theremin allows the player to select timbre and effects in real time through hand gestures while maintaining the original instrument's look and feel. The authors also provide a brief description of the design of other AI-assisted musical devices to demonstrate the framework's usefulness. Future work will involve evaluating the user experience of theremin with musicians and exploring possible modifications for performers with disabilities using the embedded intelligence system. The paper cites various references related to AI-assisted musical devices, including the Internet of Musical Things, accessible digital musical instruments, and music generation using deep learning techniques. It also mentions the importance of user experience and effective state assistant systems in AI-assisted musical devices. The authors declare no conflict of interest and acknowledge funding from the NICO project and the Daphne project. The paper concludes with a list of abbreviations and references used in the manuscript. The research presented on pages 11 and 12 explores various aspects of cognitive emotional stressors, user-centered music experiences, and accessible digital musical instruments. It includes studies on the reflective and reflexive stress responses of older adults to gaming experiences, the design of user-centered music experiences for smartwatches, and the perception of musical emotions by profoundly deaf people through vibrations. Additionally, it discusses the development of accessible digital musical instruments, including experimental evaluations and open-source projects. The pages also touch on real-time hand gesture recognition and machine learning classification tools, as well as their applications in educational settings. Overall, this research contributes to our understanding of cognitive emotional stressors and the development of innovative technologies for music and interaction.